Okay, in this video, we're going to talk about the first and second derivative tests and doing some curve sketching based on those tests. So I've given you a sketch of a curve, and I've also labeled using green and red the maximum and minimum points. So they're all vertexes, and the green is the x value and the red is the y value. So if I ask you for a maximum point or a minimum point, you would give me both the green and the red. If I asked you just for the maximum values, you would only give me the red. We're going to learn a new term today, and that's critical value and critical point. So when we talk about critical value, they will be the x values. So for right now, we're going to talk about what makes them critical values and how can I test for these critical points and critical values using a first derivative test. So first derivative tests, remember, they're testing your slope. So wherever your slope is a zero is a potential extremum. So it's a potential max or a min. But it could also be a shelf. And we haven't talked a lot about shelves yet, but we will in this exercise. So first off, tell me about the slope of the curve to the left of the critical value of -3. Do you see how the slope is positive there and negative here, and then negative to positive, positive to negative, negative to positive. So for the first derivative test to indicate an extremum, which is a max or a min, you have to have a change in the sign of the slope. And that's what we're going to look at. So first things first. Let's go to the next page. Oh, also, I noticed right here that there are no inflection points. So how can you find an inflection point? What do you think? So I'm thinking that they lie pretty much, so let's make it maybe this kind of purple. They pretty much lie right in between the max and the min, because that's where the concavity is changing. So I'm just putting 3 little lines here, and I would say that they're about where my inflection points would be. But we will discuss this on the next few slides. Okay, so looking at what it says on this bottom half of the first page of notes for 2.3, it says locating relative extreme points using the first derivative. Remember that a tangent line drawn to a relative max or a relative min point of a function has a slope of 0. So we have already drawn those tangent lines in, and I know that those lines that are tangent are horizontal, and since they're horizontal, they have a slope of 0. So I talked about already the fact that a critical number is the x value of the maximum or minimum point. So we're going to call them, instead of maximum and minimal points, we're going to call them critical points, and the critical values will be your x. So critical point, you've got to know, is going to be your x and y. So critical point is going to be the x, y. It's a coordinate pair. Critical value is just the x. So the ones that we've identified are -3, 2, and that's going to be a critical point, and -3 is the critical value. -1, -3, critical point, -1 is the critical value. The next one's going to be 2, 1. Coordinate pair, 2, 1, critical value, 2. Coordinate pair, critical points are 4, -1, and the critical value is 4. So, things that I note. Interesting, these are going to be the roots, the critical values will be the roots of the first derivative. So if I wanted to quickly sketch a first derivative, I would take those critical values of -3, -1, let's put 0 there, and then this is going to be 2, and this will be 4, and I can see that I would be able to sketch things. Now, what I know by already looking at the way the slopes have changed is that my slope is negative here. Excuse me, it's positive here, so it's above the axis, and here would be your y-axis. It's above the x-axis where it's positive. The slope will be negative here up to here. Then it's going to be positive again, go down to a 0 point at 2, it'll go negative and then come back up. So I can very quickly do a somewhat accurate sketch of my first derivative. Okay, inflection points, I already kind of drew them in, so my inflection points would be -2, -1/2, and I am kind of doing a little guesstimating here, and then +1/2, -1, and 3, 0. These would be where my inflection points are. They are also where the extremums are of my first derivative. Okay, so just good things to note. Alright, let's go through some examples. Okay, on this page, they're talking about the first derivative test. So, if I do example A says if f prime of x changes from positive to negative at a certain x equals a. So, let's say it's going to change from positive slopes to negative slope. So, if this is my A, and this is example A, then this is what I'm seeing. My slope is positive here and negative here. So I know that at A, my slope is 0. If I test, let's call this little point right here B. If I test the slope by plugging B in my first derivative, I will get a positive slope. If I test this point, we'll call it C, by plugging in C in my first derivative, I will get a negative slope. So when my slope goes from positive to negative with a 0 slope in between, I have discovered a max. So then for B, so maybe what I'll do is I'll change my color. Okay. Alright, so for B, and this will be B, they're saying that the slope is changing from negative to positive. So if I had a situation like this, where right here, where my A value is, my slope is 0, but if I test a little bit to the other side, we'll say that's my B, and I see I have a positive slope there. Oh, excuse me, I just did the exact same thing again, didn't I? Okay, so let me change that because I'm looking for a min this time. Alright, one more time. Here's a min. There's a min at A, I think. If I test right here at B, I see my slope is negative. If I test right here at C, I see my slope is positive. When I go from negative to positive with a slope of 0 in between, I've identified a min. The last case that they're telling us about is the C case. So if the slope does not change on either side of where I discovered a value of 0 for a slope, then something else is going on. So let's see what that could be. So what if I have a shape like this? Right here at A, my slope is 0. If I test to the other side of A, at B, my slope is positive. if I test to the right of A at C, my slope is also positive. So I have discovered a shelf. A shelf is neither a max nor a min. A shelf is actually an inflection point, because you see how the concavity changed? So it's concave down here and concave up here. So if you have a slope of 0, but your side does not change for your slope on either side of that 0, then you have discovered a shelf or an inflection point, and you're not going to have a max or a min there. Alright, let's go through the first example, and I'll show you how to do a sign chart as well. Okay, the first thing they want us to do is to find the local max and min points of this function. My function is a cubic. So it says take the first derivative and set it equal to 0. So doing that, I'm going to end up getting f prime of x equals, let's see, so that's going to be just x squared minus 4x plus 3. Okay, set that equal to 0, and now we're going to factor. So when I factor, I get x minus 3 times x minus 1. So my critical values are my x's, and I get those x's by setting my factors to 0. So my critical values are going to be 1 and 3. 1 and 3. My critical points I get by taking my critical value of 1 and plugging it back in the original equation for f of x, and I get a y value of 2.3. When I take my 3 and plug it back in the original equation, I get a y value of 1. Alright, now this is how you develop a sign chart. So I'm going to change my color so you can see things a little bit better. So let's put a straight line, and on the line, as a number line, write your 2 critical values. So there's my 1 and my 3. Okay, above the line will be values that are going to be the slope. So that's going to be the sine. So above the line will be the sine of f prime of x. Okay? And below the line will be the direction. The direction of f of x. Alright, so to do this evaluation, I'm going to go back to my pink color, and I'm going to say I want to evaluate a number to the left of 1. So let's pick 0. Put your 0 here in your factors, and you end up getting 0 minus 3 is a minus 3, 0 minus 1 is a minus 1, and minus 3 times a minus 1 will give me a positive value. So I have a positive slope. That is the sine of the f prime of x. It's positive when I test it at 0. So what's the direction of my function if my slope is positive? Well, the direction of my function is going to be going in this direction. My function will be increasing. Alright, now check a number between 1 and 3. So let's check 2. And we're going to put our 2 right here and right here. So 2 minus 3 ends up being a negative 1, and 2 minus 1 ends up being a positive 1, and a negative times a positive is a negative. So my slope will be negative here. If my slope is negative, that means my function must be downward sloping. Okay, so now I have a slope that's negative, my function's going down or decreasing. Lastly, let's check 4, which is to the right of 3. So when I check 4, and I put it in my function right here and right here again, I'm going to say 4 minus 3 is positive, and 4 minus 1 is also positive. Positive times a positive gives me a positive sign, positive slope of my original function. If my slope is positive, that means the direction my function is going to be going up. So now I have an idea of what's going on, because if I follow my arrows, and if I just try to draw over them in red, my function is going to be going up, reaching a max, going down, reaching a min, and then going back up. So I can approximate what my function looks like. So let me just see if I can erase that. So if I were to sketch my function, which is right here, here's 1, here's 3, I'm going to get my values, which are between 1 and 3. When x is 1, y was 2.3, and I know that's going to be a max, so I'm going to write it as a frowny face. I know at 3, 1, I have a min, so I'm going to make that a smiley face. And I know my y-intercept has to be at 1 because that's what my function indicates. So now I can approximate the sketch. So here is my approximation, which matches what I saw on my sign chart. So I need to make a statement because I can never just use a sign chart. So I would say that at x equals 1, that yields a max because the sign of f prime of x went from positive to negative. And then likewise at x equals 3, that indicated a min because the sign of f prime of x went from negative to positive, and this should be the word 2. Alright, so do I have relative or absolute maxes and mins? I would say relative because of these arrowheads. Okay, now the last thing we're going to talk about is the inflection point. I can kind of see that if I use blue, that somewhere in here, right about, whoopsies, let me just leave that be. Okay, right about here, I'm going to have an inflection point. How do I find that inflection point? Well, you take your second derivative, which is going to equal, look at my first derivative, so my second derivative will equal 2x minus 4, set that equal to 0, and you get x equals 2. So that's right here at 2. That's my x value of my inflection point. Here's my 2. Put that 2 back in the original equation, and you will get 5/3, and now you have identified the inflection point. So you have all the features that you need, and what I've done algebraically is consistent with what I've discovered through the sign chart. So we are all set and ready for another example. For example 2, they're taking us through the steps again. You will have to eventually memorize these steps, but we can use the guidelines one more time. So if I'm going to try to find the local max and minimum points without using a calculator, I'm going to take the first derivative, set it equal to 0, and factor. So when I do that, I get f prime of x equals, I have to use the power rule and the chain rule. So I'm going to bring down my 3, and then this is going to be 3x minus 1 squared times 3, because 3 is the derivative of what was inside here. So my derivative equals 9 times 3x minus 1 squared. Okay, over here now I'm going to go ahead and factor that. So f prime of x equals 9, and then why don't I just write 3x minus 1 times another 3x minus 1. So I only have one critical value, and I get that by setting my factors, and the factors are 3x minus 1 and 3x minus 1 equal to 0, and I get 1/3. 9 is not a factor because there is no x there. So my critical value is x equals 1/3. My critical point, take your 1/3, put it back in your original equation, and what happens is you will get a value of 0. Okay? So I now have a critical value as well as a critical point. So set up your sign chart. I only have one value, so I'm going to put 1/3 right here. Okay, let's test to the left of 1/3. If you take a 0 and you put it in each of the factors, you're going to end up getting -1 times a -1, which is a positive value. So I'm going to have a positive slope up above. If my slope is positive, what does my function look like? My function is heading this way. So remember, I'll just change the color. Remember that the top is the sine of f prime of x, and the bottom is the direction of f of x. Okay, so let's check to the right of 1/3, and if I check to the right of 1/3, I would probably check 1, right? Why not? And if I check 1 and put that back in the equation, I have 3 minus 1 is 2, and 3 minus 1 is 2, so I'm going to get a positive again. So if I have a positive again, then my function is still going like this. So what do I know? Well, first I'm going to kind of do my little analysis. First I'm going to do my graph, and then I'll talk about what I know. So when I'm at 1/3, and it's 1/3 comma 0, so when my x is at 1/3, what's happening is my, let's see, what is my, when x is 0, -1, I still have -1. So this is at -1, that's what my y-intercept is. And then I'm going to come here, and I'm going to gut level, and then I'm going to continue up. So my slope is positive on either side. So what I would say is that at x equals 1/3, I have a shelf, since there is no sign change. Okay? So, and I don't have any max or min at that point, so I'm going to say that I don't have one. Okay, what about the inflection point? What do you notice? Isn't 1/3 an inflection point? So don't I already have one, because isn't the concavity changing there to the left of 1/3? My concavity is concave down, and to the right is concave up. So therefore, I have my my answer already. If I wanted to back up with what I'm thinking with a second derivative test, take the second derivative, and that would equal, just look at your first derivative. Okay, so this is 18. So I have 18 times 3x minus 1 to the first power now times 3, which is 54 times 3x minus 1, set it equal to 0, and that happens where x is 1/3, which is the value I found before. So when there's not a sign change of your slope on either side of your critical value, you have discovered a shelf. So that was a shelf example. So let's go on. In the bottom of this page, we're going to speak about second derivatives. So second derivatives test for concavity, and you're going to test exactly on the value of x where the slope is 0. So, for example, if I have a slope of 0, and we'll just say this is example A, so this will be example A. If right here I have a slope of 0, and this is my A, and I take the second derivative and plug in A, and I get a negative value, then I know that A is concave down, so therefore I must have a max. So second derivative, my second derivative in this case, is going to be less than 0, and we know when the second derivative is negative, I am concave down, and I have just proven that I have a max. Looking at example B, it says that if you know that right at A, my slope is 0, if you test, so I'm going to say this, I'm testing this at A, if I test my second derivative right at A and I find it's greater than 0, then I know if it's positive and positive, then therefore I have a concave up situation. If I have a concave up, I have discovered a min. And we also said that if I find that if I test, so here I'm going, here's a shelf again, if I test right here at A and I find that my second derivative of A equals 0, I have a shelf. So that is what's happening with a second derivative. And we'll do a sign chart for a second derivative test in just a few minutes. Alright, in example number 3, they would like us to do a first and second derivative test. So the first thing we're going to do is take your first derivative, and when I take my first derivative, f prime of x will equal, let's see, 1/2 x minus 1 looks like it. So 1/2 x minus 1. I set that, 1/2 x minus 1. I set that equal to 0, and I get a critical value of 2. So my critical value is 2. To get the critical point, take the 2 and plug it back in your original equation, and you will get a value of 1. So now I have my critical point and my critical value. So I'm going to do 2 sign charts. One will be for evaluating the first derivative test, and the second one will be for evaluating the second derivative test. So my first derivative test sign chart looks like this. Get your critical value. I'm going to test to the to the left of my critical value, and I'm going to plug in, let's say, a 1. So if I plug in a 1 in my slope equation, 1/2 times 1 minus 1 is going to end up being a negative number. So 1/2 minus 1 is negative 1/2. So this is negative. Now let's check to the other side. If I plug in a 3, 3/2 minus 1 is positive. So this is positive. So my sign does change. If it's negative, the direction is going to be going down. If it's positive, the direction is going up. It looks like I have a min. So I can say a statement about it. At the critical value of 2, the slope changes from negative to positive, and therefore I have a min. Okay, let's do a sign chart for a second derivative test. So same critical value of 2. What will I do? I can check right at the critical value of 2. So I'm going to need to take a second derivative. So second derivative of x ends up being just plain old 1/2. So it doesn't really matter where I test. Wherever I test, I'm going to have a value of my second derivative that'll be positive. If it's positive, the direction that my function is going at that point is going to be an indication of being concave up. Concave up looks like that, and therefore I can say at the CV of 2, I am concave up, and therefore I have a min. So the second derivative test is this one to the right. The first derivative is this one. Don't forget, you always have to have a statement to go with it. So you can't just show me a chart. So you have to have a chart plus a statement. And both supported each other, and I have found by both the first derivative test and the second derivative test that I have a minimum point at 2, 1. So let's go on. Now we can quick do a sketch. So I'm going to just do this in the interest of time up here, and I'll just change my color so you can see what I'm doing. Okay, so what can we do for a sketch? So here's 2, 1. So if I go over 2 and up 1, and I see that my curve will go through the point 2, so here's a minimum, so it's going to go like that. So that looks like my function, and it is a parabola. So that's consistent with the function that they gave me. So I have a sketch, and I have a first derivative test and a second derivative test. And let's go on to the next page. Okay, example 4 is more typical of what you're going to be receiving. So it says, using the analysis technique previously practiced, sketch the graph. So I'm going to have to do a first derivative test and a second derivative test just to cover all my bases since I've learned 2 techniques. So take the first derivative, and you should get, let's look at that, negative x squared plus 6x minus 5. Okay, if I take this and set it equal to 0 and factor, now don't change the signs. It'll completely mess up your analysis. So factor with that negative even though we're not accustomed to doing that. So I'm going to put the negative here, and then this one will be positive. So my numbers will be 5 and 1 because that will get me what I need. So if I multiply these 2 together, I need them both to be, well, one to be positive and one to be negative. Okay, so let's see how we're going to do this. But then I want the middle to be positive. So I would like to do the following. Okay, I think I'm going to make this positive, these both negative, and this positive. Now, will that get me what I want? So that will give me a negative 1 and a negative 5. So let me see, will that do it? A negative 1 and a negative 5. So let me just think about this some more. Okay, so I've thought this through. This will work. Because look, if I FOIL this, I will get a negative x squared, which is good. I'll get a positive 1 and a positive 5x. So positive 1x and positive 5x gives me my 6. And a positive times negative gives me my negative 5. So I'm all good on that. So those are my factors. What are my critical values? So it looks to me, if I set this equal, I'll get 1 and I'll get a 5. Alright, so my critical values are 1 and 5. What are my critical points? Well, if I plug in my 1 into the original equation, I will get a negative 7/3, I believe. This will be negative 7/3. If I plug in a 5 in my original equation, I will get a 25/3, a positive 25/3. Alright, so let's do our analysis. We're going to do a first derivative test. So I want to figure out the sign. So if I test a value to the left of 1, let's test 0. So I would have positive 1 times a negative 5, and that would get me a negative value. If my value was negative, then that would be my slope of my original function is going down. Okay, check in between 1 and 5. Let's check 2. So a negative 2 plus a 1 is negative, and a negative 2 minus a 5 is also negative, so negative times negative gives me a positive. If my function's positive there, it's going to be sloping upwards like that. And now let's check to the right of 5. So let's plug in a 6. So negative 6 plus 1 will be negative, and negative 6 minus 5 will also be negative 6 minus, 6 minus 5 will be positive, so positive times a negative will be negative, and therefore I'm going to be downward sloping. So my first derivative test tells me that at x, at the critical value of x equals 1, I have a minimum because the slope changes from negative to positive. Okay, and then I would say the opposite for 5. At the critical value of x equals 5, I have a max because the slope changes from positive to negative. So the 1 comma negative 1/7 is going to be a min, and the 5 will be a max. So we're going to continue this discussion because I want to also now do a second derivative test. So we're going to do that on the next page. Okay, so I've set up the first derivative again, and now I've set up the second derivative. So what I want to do is I want to do a second derivative sign chart. So I'm going to use my same critical values that I got from the first derivative analysis of 1 and 5. And I'm going to test right on 1. So if I plug 1 into the second derivative, I get a negative 2 plus 6, and that's going to be positive, and a positive for a second derivative tells me I am concave up at that point, and that also yields a minimum. So my 5 being plugged in my second derivative will give me a negative 10 plus 6, so that's going to give me a negative value of concavity right at the critical value, and that indicates I am concave down. So I would make that statement. So I'm not going to write it out here, but what I would say is the second derivative test indicates that my function is concave down where x is 5 and concave up where x is 1. So therefore I have a min at x equals 1 and a max at x equals 5. Now I would assume that because my concavity is different, so someplace between 1 and 5, I'm going to have an inflection point. Well, where would that be? Set your second derivative equal to 0, and you get an x value of 3, and if you go ahead and plug that 3 back in the original function, I will get a y value of 3, and that is my inflection point. So based on that, I should be able to get a sketch, and let's do our sketch on the next page. Okay, so based on my first and second derivative test, I know that at the point 1 comma negative 7/5, so I'm going to just make this negative 7/5 just for ease of presentation. I know I'm going to have a min, so initially I'm going to have a smiley face that way, so I have a min. Then at 5, so this is 1, at 5 I know that my y value will be 25 thirds. So let's just make it up here just for argument's sake. This is 25 thirds. I know here I'm going to have this shape. I also know that my function, looking at my original function, where x is 0, y is 0, so it's going to go through the origin. So my function, and I also know that I have an inflection point at about 3, 3, which is going to be there. So far I can see, based on that, let's change our color, I think our function is going to look something like this. Here's my minimum, here's my inflection point, here's my maximum. So I'm looking at this and I'm saying that this minimum and this maximum appear to be relative maximums because of the nature of the function. So that was a good analysis. You should be able to do that now. Whether I ask you to do a first derivative test or a second derivative test, you should be set.